I am going to do chapter 11 again. Last time didn't quite work the way I wanted. So I'm basically going to go through every single one of these questions and make sure that we are able to do them. I did notice some really weird quick, and that is that when you do the answers for a couple of questions, there's a little bit of difference. The software says like 3.6, but the solution says it's 3.5. And I thought, well, it's probably just me because I always make mistakes anyway, and I tried it, and it kept on coming over. So all I did is I went into the settings and just told it to be a bit more generous about rounding off, because that's the only explanation I can think of, is that the software was rounding off a little bit weird. You know, it was saying a 3.5 and it should have been a 3.6. So that should be fixed for you, so that won't be an issue. So hopefully right now you're looking at question 1, and I'm just going to go through them, get these guys done, and next week we'll be returning back to the hypothesis testing. So fingers crossed, no weird software glitches. Let's go. Right, the mean and standard deviation for the height of male adults are about 70 inches, and standard deviation is 3.1. So I'll write that down. For males then, the mean is 70 inches and the standard deviation is 3.1. For females, and the mean height is 65 and the standard deviation for the females is 2.7. Okay. Then it says, suppose a random sample of 9 males and 9 females. Okay, got that. And it goes and it asks us, what is the mean of the sampling distribution and the difference of them? Well, in this case, it would be, make sure it's males. Yeah, good, males first. So it's going to be 70, take away 65, and that would be 5. Now you want to do the standard deviation of the sampling distribution. You would do that square root of S1 squared over N1 plus S2 squared over N2. Well, I could do that by hand. We've done enough of them by hand, but I don't want to do them by hand. So I'm just going to go down and find any salt button I can find. I'll use that one. And all I'm doing here is I'm letting the software do the heavy lifting. So I'm going to go here. I'm going to do, to sample, right? And I'm just going to write down the same data that I had a minute ago. So for the males, the mean is 70. And the standard deviation for the males was 3.1. And the sample size was 9. And then the second one will be the females, and that was 65. And the standard deviation here was 2.7. And the sample size was 9 again. And let's just see what else they want. Oh, where's it doing that for? All right. Right, there's that guy back. Check it. Right. And confidence interval, say 95% generate results. Okay, so they wanted to know the standard error. There it is. That means I don't need to spend all my time calculating it. So I'll do copy. I'll go here, put in the standard error. And what do they want it? 3 decimal places. Right. you round off to 3 decimal places. It's that guy. And then they give you a picture. And you want something that's got a mean of 5 and a standard deviation of 1.37. So a mean of 5 and a standard deviation of 1.37, it would look like that. And then a little sentence of it, what does it tell you? So that's question 1 done. So you see I could use salt there just to help me calculate the standard error. Now, in question 2, here is a set of data, and we're being asked to find what the mean weight is. And that question I'm not going to do, but won't you just add them all up and divide by 10? And let's pretend I knew what the answer is, and let's say it was 54. Right. Now, in this one here, you've got 2 means. What's the difference between them? Well, it's that number, 52.4, and take away the other one. So what am I going to get? I'm going to get 52.4, and 52.5 actually. So 52.5, I'm going to take away 54.7, and whatever that is my answer. So 52.4, take away 54.7, and the answer I get is negative 2.3. And I want to find the standard deviation or standard error. There's a new name for it, standard deviation. And I could do that by hand. It would be square root of this guy squared divided by 40 plus this guy squared divided by 45. But I don't want to do that. I want to use salt. Now, last time I shrank this thing up, I had a problem. I'm feeling lucky today. Oops, needs to be just a little bit more. Right. So the mean is 52.5. Standard deviation is 2. They're calling it sigma, so evidently this is a population. But you're still taking a sample of 40 from it. And the second one is 54.7. And the standard deviation is still 2. And there's 45 of them. And generate results. Then I move over here. And there's the standard error for me. So if you don't want to do big, ugly calculations, yeah, you see, I can't count. See, the difference was negative 2.2. And that's that one done. Okay, on to question 3 then. 45 men. I'll just keep that there. There we go. Move this to the right. Open this. Open this up a touch. Okay. So in this sample, there are 45 men, 57, 1.8, 45 women, 54, 1.9, and we're going to do the usual 95% confidence interval. So I should just go over here and just try to make sure it's men take away women and not the other way around, because they do that to me sometimes. Good, men take away women. So get the numbers, and the first one is going to be men, so there's 45 of them. (57) is their average head circumference. Standard deviation is 1.8. 45 women. Okay, it's already here. What else do we know? 54.4. And standard deviation for the women, 1.9. I should be able to just go down here, generate results, and then see what we have. So find the difference, 2.6. There we go. Standard error, that guy. To the nearest tenth, so that's 0.4. 95% confidence, that guy. To that guy. Rounded off to the nearest 10. Are we comfortable with these ones? This is how it should have worked yesterday. Right, you just put in the data in the storyline, and over here on the right hand side, Salt should do all the good stuff. Can I bypass 4 because it's pretty much the same? You want me to do 4? Or are we okay with just saying it's same as the other one? I wish I had more pictures. I could tell by your faces whether this is okay. Okay, if nobody says they'd like to see 4, I will move on. In this question, there is no salt because actually it's a whole load of reading, and it comes to this part here. Suppose a 95% confidence interval for the difference in the population means from positive and negative feedback groups was found to be somewhere between 0.52 and 2.42. And then it gives you basically 4 sentences, one of which is the truth. So we can be 95% confident that the true mean difference between the groups would be between there and there. I like that one. I like that one. So moving on. Only got a few more questions and this is essentially done. This one did have something in it that was kind of weird, or not obvious where the answer was.
Yeah. When Mom and I play.
Hello. I will try and talk over those people for a moment because there we go. I'm sure we don't want to hear the conversation. So we got question 6. And I said this one is a little bit weird at the end, and it is, because everything you need to know is actually here. It's almost like they did Salt for you. So what we have here is the testosterone levels of men in 2 different professions. The researcher suggested that there are occupational differences in the mean testosterone level between medical doctors and university professors. If I believed that that was actually true, that the testosterone level of people in certain professions was different than others, I wouldn't have picked those 2. I would have probably picked professional boxers and nursery school teachers. I would try and find 2 professions or 2 jobs that to me would be bigger extremes. I'm not sure these 2 groups would be that different. Right. So anyway, 16 doctors, that's the mean standard deviation, and that's their mean, that's their standard deviation. The difference between them is 1.1. And not surprisingly, the confidence interval has negative and positive numbers in it and the degrees of freedom are 22. So what are the questions? There's a 95% confidence interval and it's unpooled. So which one of those guys are you going to use? And the answer is you're going to use that one. What is the statistic? The statistic is that guy. So it's really terms. What is the standard error? Well, actually, the standard error, as far as I can tell, hasn't been mentioned. I mean, they do the standard error separately, but they don't do the difference one. So I'm going to use salt. Okay, where'd you go? Oh, there you are. And I'm going to put in those numbers so that I can find this guy. So there are two groups here. There is 11.7. Standard deviation, 3.37. No. Yes, it is. And sample size was just 16. And you go down here, you do this one, it's 10.6. 2.56 and 10. And keep everything the same. Generate results. Make sure I did it. Generate results. Move over here. There's the standard error. And what do they want? 2 decimal places. And then they have the guy called the multiplier. Can you remember that multiplier was that little guy we called T star? And this one is a 95% confidence interval, and I don't know the multiplier yet. So I'm going to have to hit this fella again. I'm going to go hunting for it. So it's going to be a distribution calculation. T-distribution. Degrees of freedom. Well, they told us up here it's 22. And I am looking for a 95%. And if I go over here and you see a little picture, if you do 95% in the middle, that leaves 2.5% either side. So I go here and I say, I want 2.5%. And the number I get, forget about the sign of it, is 2.07. So the multiplier is basically that number there. And of course, there'll be a 1 over there that's positive. And both numbers are 2.7. And then the rest is pretty straightforward. Next question. Same situation where you've pretty much been given all the data. And this one is to do with using your wrong hand to write letters. And it says, what's the mean number of letters printed? Females. For females, it's that number there. Oh, am I not allowed to copy and paste? That's annoying. Thought I could. Oh, good, you can. Males. So it looks like there's a difference between dexterity. What's the difference between them? So it's really just knowing where to look on the table. What's the 95% confidence interval? Well, starts on that number and it finishes with this number. And then a little sentence and a little picture and so on. Now let's focus on this one. So the story is, you use your non-dominant hand. So if you're right-handed, you use your left hand, and whatever it is, 15 seconds, you write down as many letters of the alphabet as you can. And typical female gets about 12 letters done on average, and a typical male does about 13. There looks like there might be a difference between them. When you do the confidence interval, it ends up being this. That interval contains 0. So the gist of the conclusion is that you cannot tell. So you cannot tell. Right, and the stuff down here, this fella here is simply just calculating the standard error. So you would do it over here. And this one is finding the multiplier, T star. And we just did one with them a minute ago, right? That one there, for instance. And then the last question is pretty much like all the others. Okay, so I feel a little bit more comfortable that that has worked. So, is there any questions that you want me to go over before we return to hypothesis testing? Are we good? Right. Glad I got that awkwardness out of the way. We did hypothesis testing yesterday, and we're continuing with that today, but we're in the introductory stage. So let's get some practice at finding the null and the alternate hypothesis. So you get a story, and the story kind of has this kind of theme to it. They all kind of, in a way, sound the same. They're going to begin by telling you something that they believe is true. So I believe that in the year 2000, right, let's suppose that we know for a fact that the percentage of people who watched American football was 37%. So the percentage of adults who would watch American football on TV was 0.37. You think of that, this is going to be the null. This is what is true, unless you can prove to me otherwise. And someone has a question based on that. They don't think it's true anymore. They don't think 37% of Americans watch football. They think it's gone down. So their conjecture is gone down. So in that story, the first thing you would set up is your null and alternate hypothesis. The null is 0.37, and the alternate is what you believe is now true, right? So my conjecture is that it's less. And that's it. It's not difficult, right? There's something that's true, that's the null, and somebody thinks it's different in some way. And there are 3 versions of hypothesis test. There's version 1, is that we believe it's this number or it's going down. Let's suppose in the past, the probability that you were undernourished was 11%. So 11% of American adults were deficient in something, right? Undernourished. And we believe that today it's gone up. It's gone down. Oh, actually, yeah, too late. It's gone down. So the null hypothesis is that it's still the same number, and the alternative is it's gone down. Right, let's do a going up, because I wanted to do a going up actually. So something that's got more than it was, right? In the 1800s, 70% of adults were literate. I think it's gone up. Well, the null hypothesis then is what it used to be, what we believe was true, and the alternate is that it's gone up. In the year 2020, the percentage of people who believed that politicians were generally nice people was 31%. And I now believe that it's changed. I'm not quite sure how it's changed, although I have my own opinions, but let's pretend I don't. I just know it's different. And so what does that look like? Well, the null hypothesis is always going to be what the status quo is, what it used to be. And the alternate is what we think it's now. And in this case, we call it a not equal to. So there are, in fact, and I'll put this one down as my third one then, there are, in fact, only 3 kinds of alternate tests. Of all the ones you could do, these are the 3 for a single proportion. You think it's going up, you think it's gone down, or you think it's changed. And we have names for each one of these. This one is called a right-tailed test. So it's a hypothesis test, but this one is called a right-tailed hypothesis test. This one is called a left-tailed test. And this one is called a two-tailed test. Are you comfortable that if I gave you a story like, you know, literacy or people's opinion in politicians, or I can't remember what this made up story was, but something has gone down, that you could create these 3 guys? So we're spending today, at least a part of today, on the terminology that is used, the vocabulary. This guy here, the 0.7, in this case, the 0.31, and in this case, the 0.30, this is called peanut. That is the symbol that we use for the number that goes here. It's called peanut. It's also got a name. It's called the null value. So if you get a question and it says, what's the null value? They're asking you to tell me it's 0.7 in this story, or it's 0.31 in this story, or it's 0.37 in this story. So the null value is the decimal that goes with the H naught. And I did mention it yesterday, but I guess I should put it in here since I'm doing vocabulary. The H naught is called the null hypothesis. And HA is called the alternate. You okay with these terms? Just things to remember. So let's do a start to finish. Yeah, we've got time. Let's do a start to finish story like we did yesterday. So let's suppose, what shall we do? In 1990, they did a large survey and they found that 21% of Americans were overweight, right? Their BMI index number was greater than whatever they decide obese is, right? Overweight. And so medical people got a grant off the government, which is kind of how a lot of these things work. And the government said, I'd like you to check in again, see if there's a difference. And the guys are looking around and they say, yeah, I'm pretty sure there's a difference. And so they think that it is now larger percentage. If I bet you right now, I haven't read about it, but I bet you right now, there's a hospital somewhere or a clinical study somewhere being done on the health of people before COVID and the health of people after. Anybody heard the phrase COVID-19? Yeah. Have you heard it in this context? COVID-19 is a phrase that's going around, and it's not to do with directly the COVID or the version of COVID. It's to do with the fact that a lot of people over that 2-year period have gained weight. And it's COVID-19 because, like in a joke, they think it's increased by 19 pounds. Right? People have got heavier. Why? Because they're at home more. A lot of you were working at home, and so it's much easier, isn't it, just to go into the kitchen when you get a break, grab something, you know, a nibble that you shouldn't really need, but you're just bored. And people have gained weight. So it is, you know, it is very likely. And if it's not, I'm surprised that they're doing a survey right now on various things like the weight of people during the COVID period. So back to the story. We now think it's a larger percentage. So how would we set up a hypothesis test? We would say the null hypothesis, based on data that we have collected in the past, is that the percentage of overweight American adults is 21%. In this story, we want to prove that it's gone up, because we're sure it has. So that would be your first step. Just get this thing. Now, at this point here, you need to choose a significance level. It's called alpha, and it's a small number, and it typically is either 5%, 10%, 1%. They're the most common values for alpha. Alpha is the number that you're willing to live with, because alpha is basically the percentage of times that you are going to get your hypothesis wrong. In other words, you're going to say, yay, hey guys, I've proved it, but you were wrong, right? You had it. you proved it, but it wasn't really true. And in every hypothesis test, once you've decided what this is, you should then move on right at this point and choose that. So how do they pick it? It's a judgment call. I'm going to pick that one. So if at the end of the day, I end up saying, I've proved that people have got heavier, and the statistics say that, and it's valid, this little addendum, but there's a 1% chance I just got it wrong. Nothing in statistics is 100%. That's not the way the world works. We take the data and we do the best we can with it, but we're going to be wrong some of the time. The best we can do is to make sure that we're wrong as few times as possible, right? So let's move on then. What do we do? Well, once you've done that phase, I guess I'll call that phase one. So phase one is null alternate hypothesis and choose a significance level. Phase two is you collect your data. And we'll assume that it's good data and all the other unbiasedness about it. And let's say in this story, we collected a sample of 1,000 people. That's a good, decent sample, 1,000. Very common number actually for samples. And in this sample, we measured the weights of people and we did that BMI calculation and we compared it against the number that you need to be overweight. And at the end of the day, we got .23. So 23% of Americans are overweight, at least 23% of my sample. And because it's a sample, we put the little p hat on it, right? That's the symbol for sample proportion. Now, if you look at it, you might say, well, time to walk away. 23%, bigger than 21. I've proved it. No, not so quick. We know that when you take samples, there's always variation. 23% is bigger than 21, but couldn't that just happen by randomness? I could take another sample of 1,000 and it was 20% are overweight, right? Could take another one and it's 24, take another one and it's 19, right? Samples vary. And so we have to do more work than just get this number and stop. But we have collected the data. So there's phase two, done its job. When you're doing a hypothesis test, other scientists are going to look at your data and they're going to look at how you set it up and how you collected it. So you make sure that you've got these kind of nice lined up in a row and they're going to say, okay, I understand why they're doing this. I like that number, it's nice and small. So that if they get a conclusion, it's going to be 99% of the time, it's going to be right. Yeah, I like the sample size. I'm assuming that they told the truth about that. And we'll move on to phase three, which is basically going to be the calculations. So we've already got p hat. We need to find the standard error p hat, which is can anyone remember, because we've used this formula in all sorts of other ways, what the standard error for p hat is? What's the formula for it? I'll start by giving you, it's a square root.
P hat times 1 minus p hat over n.
Have you noticed that it's like a bad penny? Doesn't this formula just keep on turning up, right? but it's a very useful formula, right? It is used in lots of ways. Standard error. We're now going to get one more guy. He's called the Z-score. One more calculation right now. He is called the Z-score. And it is equal to, and I only wrote it down once yesterday, so I'm pushing our luck here. But can anybody remember the formula for getting Z-score?
It's x minus the mean over the standard deviation.
That is correct. That's the general version. But in this case, I want you to use standard errors and p-hats and p-naughts. So p-hat, which is your data. P-naught is like your mean. And SE of p-hat is like your standard deviation. So it's still data taken with the mean divided by standard deviation. But in the context of here, do you see that each of those things has got a different name, right? That's your data. That's like your mean, and that's like your standard deviation, right? They do the same kind of jobs. So in this case, the standard error then, and I just put p-hat in here, and I am glad I caught myself, because you could use p-hat, but we don't. Which guy do we use? You use this guy. So it's actually p-naught that we use. And p-naught is 0.21. And take 1 away from it and you get 0.79. And you divide the whole thing by a sample size of 1,000. Square root of 0.21 times 0.79 divided by 1, 2, 3 zeros, and you get 0.013. So since I don't have room here, I'll squeeze it in over here. 0.013. So the Z-score is p-hat, which is this number, take away p-naught, which is this number, divided by the standard error, which is this number. And let's just do a deliberate mistake. 0.23, take away 0.21, divided by 0.013. And that number is weird, and it's also wrong. What did I do wrong in my calculator? This is the calculation I want to get the answer to. It looks like I've typed it in, but I haven't actually done it right. What's missing?
It
Brackets.
divided only by the 0.21.
That's right. So to make that happen, you have to put brackets around it. And the number I got here is 1.538. So phase 3, we've done our calculations, right? We've got our p-hat, we've got our standard error, and we've got our Z-score. Phase 4. We're now going to find a guy called p-value. This is a probability that you got this sample when the original information was true. So what's the chance that just by randomness, you got this sample? That's what the p-value is calculated. In our story then, the p-value is going to be the probability, right, that you got a Z-score greater than that number. Now you may say, well, why isn't it less than that number? If this guy, your alternate is you're trying to prove something's bigger, then you're trying to look at z-scores being bigger, right? Now this thing here gets done in sol, right? So you're always going to end up using sol. Even although you do everything else by hand, this last bit is kind of has to be sol.